Thank you. I'm gonna live up to that door. I thought I was only known by the FBI. Anyways, uh, Mickey, everyone NKY is my wife, and she helps me with this sometime. And we live in Henniker on Craney Hill. You might hear me on 146.52.
29 a month.
I'm known as a guy that doesn't usually do this. Not that I'm against it, but I just don't do them. And one of my good friends, Chris Lumen, is here, 86 CIH. We're in a VHF contest. You might have worked with one of us. Chris helps me with my score because he has 10 bands, 50 megs up to 10 gigahertz. He has a mobile truck that goes rolling, goes from grid to grid. So that's a lot of multipliers. I can work Chris on several grids, and I help him too. So it's kind of a mutually beneficial thing. So we're both into that sort of thing. And your club seems to have a really variety of pretty interesting things that you do. I applaud you for doing that. And I applaud you for getting new people involved with ham radio because, once we get older, we need people to take over and do things. But I think the coda and soda things have really caught on. Chris is into this. He's soda, right? And field day, what can I say? I haven't missed it in over 60 years. I have not missed a single field day. And so look for K1B. We're doing it at my house. We're doing the Class E, which is not cheating. It's emergency communications that we get. They get too old to put towers. I don't see very well, but so when I ask the question of the audience, instead of just raising their hand, I'll see as a word. Just say something. You can call, whatever. It's a family show, so be careful what you do. And so I'm going to ask a couple of questions. First of all, how many people here are not licensed? Anybody good? One. Okay. How many people are pretty new hands? So rest of the year. Okay. So I'm trying to figure out what kind of audience you have. How many people have been licensed for 50 years? A few. All right. Sounds like we have a variety. So what I don't want to do is bore people, make them not too simple, but I also don't want to leave people in the dust either. So this is kind of a visual thing. Unfortunately, I guess we can't dim the lights. They're either on or off, so this may not be as suppressive, but you'll have to live with it. If you turn the lights off, I can't do nothing with everything. Huh? All right. So we could turn them off instantly. So what I'm doing is a visual demonstration without too much math, but I'm going to get rid of the math. Oh, that's good. Let's manage that. That's good. That's good. So somebody lied to me. They said it's either on or off. All right. So I am going to show you some antennas, but they're small because I have to carry them in the room, right? And with small antennas, you can build many versions without spending a lot of money. They're also easy to make physically because they don't need fancy insulators and expensive wire and all this and that. So most of this is wood, dowels, number 14 or number 12 wire from Home Depot or someplace. Get the insulation off, and you can make these antennas. And in this case, it's aluminum rod. Rod. All stuff you can work with. The purpose of the wood is just to hold it together. It's an insulator. So if you're a real neophyte, you should realize that the wood is not essential for the performance of the antenna, but it is essential mechanically to hold it in the right position. So you'll see wood and wire. And you can make any antenna that you read about and rule over that you might want to use on, say, 80 meters or 20 meters. We can make a small version that's 70 centimeters, or it's much smaller. See how it works. And if you like it, then you might have some confidence to probably work on the band that you want. So if you're into HF, think of these things on a much larger scale. You have to think in terms of wavelengths to appreciate this. I am doing most of the stuff at 432 megahertz because I have it. But I used to do EME, Earth, Moon, Earth, And I have a transverter and so on. And plus, the size of the wavelength, 70 centimeters, is kind of convenient. If I tried to do it at 1296 megahertz, it's not to get too critical. If I do it on 2 meters instead of 70 centimeters, it'd be 3 times as big. I couldn't carry as many things in a room. So 70 centimeters, you're not metric, is a little over 2 feet, about 6 or 27. Anyways, some basic stuff. Hams talk about decibels. So I just have a handout sheet on that. Some of you, most of you probably know about decibels, but some people may not. It's a ratio. Decibel is a ratio of power. It's the amount of increase or decrease of something. So when we talk about so many decibels, like the coaxial cable every loss, the loss of so many decibels. And your antenna might have a gain or an improvement over something that we have to prescribe of so many decibels. So originally, this was something that Alexander Graham Bell inspired. I don't think he named the term. And I don't understand. Maybe somebody can explain to me why it's spelled B-E-L instead of B-E-L-L. But he was working with deaf people and he was interested in measuring sound ratios and that sort of thing. So they named the unit after him. It's a logarithmic unit. If you go to take a test, like an extra class test, I think they may ask you some questions about decibels or problems with anything. You don't necessarily have to know logarithms to do this. You can pretty well estimate to the nearest decibel. A decibel is a tenth of a bell. Turns out that a bell is an increase of 10 times. So if I go from 1 watt to 10, 100 watts to 1,000, that's a 10 decibel increase. Or one bell. A decibel is a tenth of a bell. And in sound, it's probably about the smallest amount of change that the human ear can detect in terms of frequency. So if you went 1 decibel stronger, you feel the slight increase in sound. So we talk for some reason about decibels rather than bells. And I use this magic number that you won't see in the text. It's 1.26. That's it. 1.25. Each decibel is that much stronger in power than we have. So if I had 1 watt and I wanted to go up 1 decibel, it would be about 1.26 watts. And if I went from that number of watts, 1.26, to the next decibel, if you multiply that times 1.26, you get 2.58. If you keep multiplying 1.26 times itself 10 times, you end up with 10. So this fills in the spaces between 0 dB and fills in the spaces. So you can pretty well, using that number, pretty much figure out what is decibel. It's not exact. It's a logarithmic. You can decrease it by 1 over 0.79 times its scale. So if I wanted to decrease, like I had coax loss of 1 dB, typical of a piece of RG8 table on HF, 1 dB of loss. If I put 100 watts in, I'd get 79 watts at the other end. Where's the other 21 watts? Heats up the coax. It's expensive radio energy that's being wasted. So you want to keep your losses of cable down pretty low. I'm using some fairly lossless cable, but I don't have long runs of it. And it's easy to work with. So that kind of outweighs the fact that I've got loss. I don't really care. I'm just going to them. So decibels are important. So you add decibels. It makes it a lot easier, but you multiply the power ratios. There is a way to convert power to voltage or current as long as you have a 50 ohm system built in or some other standard. You can do that, and I don't usually do that, and it's not done on the right. But you'll see that once in a while. Now, antennas are often compared. Well, I'm going to get into this. I'm going to leave the subject. Any questions on decibels? I'm told that I've got about an hour or so. You have to drag me out with a book, so I'm going to try to keep it short. But believe me, there's more info than I could possibly cover here. So we're just doing a little bit of a survey. If you have a certain amount of energy and you put it into what we call an isotropic radiator jet, Does that name sound familiar from exams? We talked about that. Anybody? I don't know if it's still on. Here's an example of a not too good isotopic radiator. It radiates equally in all directions. I'm a foot away from this light bulb, the brightness of the sun. But it's not a real isotopic radiator. That's a theoretical idea. Why isn't it real? Why can't I give it to you? You're talking about suspended in space. All right, good, good. 2 points. The cable coming out leaves a blind spot, kind of like your optic nerve. You can't see in that direction. You're blocked by it. Here, the stem blocks it. I suppose if you put a battery inside of a light bulb, you can remove that part of it. But what about the space part? What's that mean? Are we in space? No. If I go far enough away from this isotopic radiator, what do I run into? The floor. So at least half of the light's going to get blocked. So it might be like a half sphere. So closest thing I can think of to an isotopic radiator might be the sun, because it's suspended in space. But even that's not perfect, because sunspots and everything else make it uneven. Energy is not evenly. So it's a theoretical idea. Now, as hams, we usually want to talk to a friend or somebody or edge contact or something. We don't want to spread our very expensive energy all around to everyone in the universe. We want to direct it. So we have to take some of that energy, put it where we want it, but we can't get something for nothing. So what happens to the rest of it? We take it from someplace and put it where we want it. And the amount of an improvement you might get as far as brightness, we call gain. Gain is like an improvement. It's also a detergent. I don't think that has anything to do with it. So, but if I get gain in one direction, like I want to talk to someone in the back of the room, you'll get me stronger, but someone else can not get it so strong. So that's one reason why we sometimes use directional antenna. All right, an example of, and I'm showing this with light waves. Light waves are related to the waves. You ever play around with optical stuff, you're aware of that. Anybody got a couple of reasons that they might be similar? This, you can see the radio waves. They're all electromagnetic. Did I hear that? Repeat it. Particle and a wave. How about the speed at which they travel? Speed of light. Radio waves travel the same speed. They can get slowed down, and they will if they go through a medium like plastic, air, uh, or if they're near metal. But speed of light is pretty fast. I know what it is. Yep. All right. I hear two answers. 186,000 miles a second or 300 million meters per second. That's pretty fast. Now, some people, you can correct them on this, think that sound waves and radio waves are the same thing. Here's a sound wave. You have a tuning fork? How fast does this sound? 600 miles an hour? How many feet per second? 700, somewhere around 1,000, whatever. That's very much slower than the light. And what happens if I take the air out of it? Two things. All right. You won't hear it because it needs something to vibrate. And somebody pointed out you'll probably die. So two things will happen. So sound waves are very much slower than radio. And to go around the world, this would take radio waves to go around 7 times in a second. That's a lot of difference. Now, as fast as that is, when you do radio astronomy or you're looking at stars, you're seeing things that happen light years away. The amount of time it takes the light to travel here, it's about 6 trillion miles, I think. And when you get the new telescope that can see things a million light years away. That means that what you're saying happened a million years ago, and it's reaching. That's kind of mind. I like to think of our radio programs in the early days, 100 years ago, radiating out into space, and somebody 100 light years away just got to pick up music from the 1920s. That's kind of a big job. They can't tell us what they heard, because we won't be around to get the answer. All right, so any questions on that? Electromagnetic waves, we put alternating current into a wire, you can generate them. They have an electric component and a magnetic component at right angles to each other. And I show it as these sine waves at right angles. So we usually think of the electric component as being parallel to the wire in the antenna, and the magnetic component is being perpendicular to it. And because we're standing on Earth, a horizontal wire to us means it's polarized horizontally. And that's the electric part. The vertical part, the up and down part, the roller coaster is the magnetic part. And they're moving out at the speed of light. So the two things at right angles and the direction that travel at right angles to those two. The fancy word is orthogonal. The three things at right angles. So these waves, now, the light waves that I showed you, not polarized, because they're all randomly mixed up. There are polarizing filters and so on that you can use to select horizontal or vertical. This is another point. Right? So I'm going to put some energy into one antenna. 432 megahertz, a little more than that. It's something that every ham should know how to do. Frequency and wavelength. Wavelength is that Greek letter lambda, or lowercase lambda, which is an L in Greek. If you divide the frequency, the number of cycles per second, into 300, let's say, frequency, megahertz. With the 300, you will get the wavelength in meters. And if you divide 300 by the wavelength in meters, you'll get the frequency in megahertz. That's simpler to use than 300 million. But I already get it incorporated into megahertz part of it. So you can find one if you know the other. And they're reciprocal. So if the frequency gets higher, in other words, more cycles per second, the wave gets smaller. The waves get shorter as the frequency gets higher, and vice versa. So I'm dealing with what's called ultra-high frequency waves, UHF. They vary between 300 megahertz and 2,000 megahertz, and they cover a few ham bands. 432 megahertz is the lowest UHF. We have UHF TV. And in that region, we have antennas that can be made smaller. And that's fun to experiment with this stuff. We can do a lot in a room. So 432 megahertz. So I'm going to, here's a directional lightning. The magnet, right? And not very good. Oh, there we go. I can change the focus of the thing and spread it out, or I can concentrate it. Kind of hard to do in the light, but that's all right. Anyways, I'm directing energy that way, but I'm using it in other directions. Well, the number of degrees that cone covers between the points where the power drops to half, which is 3 degrees, 3 decibel, 3 than the maximum, is called the beam width, which measures in degrees. There's 360 degrees around the circle. So if I had a beam width of, say, 30 degrees out of 360, that would give you the beam width. Usually considered the minus 3 dB points from the maximum to the middle. If you want to make the thing brighter, you have to focus it sharper, you might end up on, say, 20 degrees. Some of the stuff that people do with lasers is fractions of 1 degree. Lasers are pretty hard to break. Typically like 0.05 degrees pointing a laser. That's pretty sharp. So, with that in mind, here is a radio equivalent of my magnet. It's called a Yagi antenna. It's a bunch of wires that get progressively shorter and they act as focusing element. What they do is they slow the radio wave that's coming out almost at a plane at a distance, like a flat plane moving over. They put a dimple in it and they'll either spread it or compress it, but they don't know the way. But compressing it, they focus it, they slow the middle down more than the edges. So it puts a bend in the wave point as it comes at you. It makes the energy all focused towards the point. So when you're receiving energy on this antenna, it'll go that way and it'll focus on this copper element, white copper, so it'll start it with it. And that's called the driven element. When you transmit, you're driving it. The others are called parasitic elements. They're not connected. They're parasitic. They just sit there and act as focusing elements, or like little lenses. And in fact, in theory, you could make a light. You could deal with something microscopically small. You could make little tiny directors and things on wire. I don't know if I've done that. You could. Conversely, you can use a lens like my maglite on radio waves in the upper microwave region where waves are so small that start to behave that way. And you can actually use a glass or plastic lens when you get up at the done it at 47 gigs and 122 gigabits. Right, let's put some energy to this thing here. This is the transfer. If you want to know, I'm putting out just a few watts here. And here we go. So that energy is focused in that direction. And let's see if I can put up some energy on this little light bulb. Can you see that? I got to be careful because I don't have many lamps. I used to let the audience do this stuff and blow them up. And the Radio Shack lamps, I don't think we can do it. But this antenna is a dipole, two poles, right? And it is a half wavelength long. Half wavelength. Turns out that during half of the alternating current cycle, electrons go in one direction. By the time they go from this end to that end, it's just enough time for the cycle to reverse directions because it's alternating current. And they have just enough time to get there, and then they punch up and go this way. They just have enough time to reach that end. So the length is sort of time to the frequency, the wavelength. Much like a pendulum on a clock. Also, that's there are a lot of things in nature. They're called resonant or tuned systems. One I can think of is the Bay of Fundy in Maine. It happens to be the right size physically so that when the tides, if you depend on the moon and the sun, when the tides go in and out, they reinforce each other because they have just enough time to reach the 200 miles before the next one comes in and adds to it. This is why you have these high tides. I think there's another place in Japan. So that's a resonant system, a swing, and a pendulum do that. Give it a kick at the right time to reinforce it. If you have people marching in a parade and some of them are out of step, you're up with a mess. But you want them to kind of reinforce it. So this is why the dipole is a halfway long. Now, horizontal. So what polarization? What can happen? Right. Comes back. It matches that. The electric part of the wave is parallel to the wire. Because we're standing on it, we call it horizontal polarization. It doesn't mean much in space. If you want to turn it this way, I'd have to turn this one this way. Get the energy to hit it right. And that would be vertically polarized. Everybody see that? Goes away. Right. Now, hams don't like doing the same thing as each other. So we have different camps who prefer one over the other. I'm of the single sideband CWDX kind of world. Most of us use horizontal polarization. Yes. Yeah, ask questions anytime and just yell. What power? A few watts. I think between 2 and what have I got? Yeah, I think it's like 2 watts. I can change it. I can suggest it. Yeah, it's not 3 watts. By the way, this lamp is only 1.5 volts or 50 milliamps, so it's like 25 milliwatts. Obviously, I can't get more into this than I'm putting out there. The room dissipates some of it. So you never get more than you start. So if you want to try running a 1,000 watt lamp, I wouldn't be in the room. You'd have to run a lot more than that out of the transfer. But in theory, the energy would keep going on and on forever. Notice there's some bright spots, green spots. In theory, it's supposed to diminish the square of the distance because it's spreading out in both directions. So you go twice the distance, you should be getting 1/4 the power because it's going horizontally vertical. You go 10 times the distance, you should get 1/100th of the power. This thing has an area around it that it collects energy. It's called an aperture, or capture area. It wants to catch all the energy it can in that area. So I can I can show you the effects of the room. In fact, there's something interesting that's different between light rays and that. That is the fact that it can go through cardboard. Can't see through it, but the radio wave, or some insulating thing like it goes through. And that the amount that it goes through is sort of dependent on the frequency. We don't have to go up and microwaves. Buildings that are microscopically big end up blocking it, moisture, so on. All right, Chris, you want to help me here? Chris is going to be my helper. See, I don't want this anybody to do this. He's trained. You're gonna sort of, you're gonna kind of walk around behind me. You get closer and further. Everybody see that? Keep going. Yeah, you get right in line with it. Yeah, in line with it. What are we doing? Keep going. Get closer to me. Everybody see what's happening? Right? Dimmer, brighter and dimmer. What do we have? Reflecting, right? And that blocks it. All right, so if you get as close as you can to make it bright, keep it even closer. There you go. It's getting dimmer. You get a quarter wave away. The signal has to travel an extra quarter wave from there to reach that reflector, and it does this. But then it has to go back and gets bounced off, and it's like a mirror. It looks like a mirror image, and that image is out of phase. You picture up there? But it has to travel a half wave physically because it goes a quarter wave to the reflector and another quarter wave back. So, but because it's reversed, that extra half wave instead of subtracting from it is added. So the reflector a quarter wave away acts like something that reinforces the wave. Now, try it again. Only this time go even further back. Right. Every time you move a half wave away from that quarter wave distance, you have to repeat, you get another peak. And every time in between, you go like here, a half wave ago, you should get a null. There's the null. So that's a half wave. That half wave plus the half wave physically coming back plus the reversal of reflection puts it out of phase. Kind of neat, huh? So you can make a reflector. Sometimes you don't want to. Like if you got wire in the house or a gutter, you can't get out on some fan, you probably have a reflector. All right, so I could do the same thing by I have a wire that the thing is to reflect it. Right here. You do the same thing with this piece of wire, which is a little bit longer than that dipole. It's about 5% longer. A lot less metal, but it is. In fact, you want to hold this. Either one, just so everybody can see it. In fact, do both of them. Don't turn it on. Let me speak to you again. No, I will. I need your points in the contest. All right, let's get it. Let's get it bright. All right, I can detune it. Why? I can detune this one. I had an extra quarter wave of wire. All right, so this is something you should think about because if you have small antennas on your roof and a big bird sits on them, they can detune it, or an icicle, or snow, or all kinds of things. So as they get, because the antennas are small compared to the objects around it. You can do this at home. You have fun with it. You learn a lot about how you can get a feel for this stuff. All right. So I'm going to stay there. I'm going to do the same thing here. I'm going to detune this one. Yeah. If you make an antenna, when you start doing things like this and it gets brighter, probably that's something that needs to be improved on. So every one of these things, if it's optimized, is going to only get worse. But all right, now I'm going to show you the beam width idea. All right, now so say you've got a certain amount. I have a meter of measure what. And I move this thing till it goes to half brilliant, measure the number of degrees, and then I go on the other side and measure it. Measure the number of degrees. The beam width is the distance between those 2 points. That's called a horizontal beam width because it's horizontal azimuth. But we also have an elevation beam width, which is but anyways, that's the vertical beam. With the Yagi antenna, it's usually wider vertical, so perpendicular to the element. It's only slightly. So we got two beams. That's called the elevation. So you get azimuth and elevation. Anytime you make an antenna, you want to study propagation of radio waves and how they travel, you have to think about where they're coming in and whether they're going to be within the beam width. If you want to talk to somebody in Europe or Asia, the signals are going to come off the horizon pretty low. So they're going to be skipping off the ionosphere. They're not going to be too many degrees above the horizon. But if you want to talk to your friend using what's called NVIS, near vertical incidence, the signals may be hitting the ionosphere, but the guy's only 100 miles away, up overhead and bouncing down. So they're going to be coming in a high. So this antenna would have to be pointed up for that. So you got to think about all those things when you decide what antennas operate, what you're trying to do. Right? I mentioned that the FM and people use vertical polarization. We'll get into that in a few minutes. Let me make a diversion here, and I'm going to have Chris hold the light bulb. You don't need to put the reflector on here, and just get it to light up somewhat. Now I could send. There you go. I could send to Chris. You wouldn't want with it off and on. A, B, 6, C, I, H. That would be even fun. A, B. There you go. All right. I could send code. Not everybody can copy code, but I could also talk on a microphone. So I'm going to put a little bit of signal on here. Let's call it carrier. I'm going to turn it down a little bit. I'm going to turn the microphone in, and I should see the light get brighter. And that, you can't hear that, but that's going to match the pattern of the voice. But if you don't believe it, I'm going to give Chris this. How many people have ever built a crystal radio? A lot of people. How many people have ever built a crystal radio that works 432 megabits? I didn't think so. Well, this is one. All it is, the diode, a little matching thing here. The word crystal comes from the fact that they used like galena or lead or something that actually a crystal that would conduct one way and not the other. But now we use a diode, and I have a little transformer and speaker. So just go on to that, and I will talk to you. This is not the VX champion radio of the world, but hello, 1, 2, 3, 4, 1, 2, 3, 4. Anybody hear that? Pass it around to people in the front there. All right. So what I'm doing here actually can prove useful. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. You can have fun with this stuff afterwards. But I was doing this once in Concord at the McCollum Shepherd Discovery Center. My friend Emily JHJ was listening from his house. He could actually hear me several miles away with this setup. And so, in case the FCC is listening, this is AF1T, or ID. 1, 2, 3, 4. Right? So it is useful. Right. Now, I'll get your interest peaked. I'm going to crank the power up a little bit. Everybody got it? Pass it around more? All right. You all keep playing with that? Anybody else want to play with that? All right. Why not? What can an antenna be made of? I'm showing copper, aluminum. What will work? Anything conductive will work as an antenna. It may not work well, but it will work. So let's see if we can do another example of something that might be fun to play with. You ever have if you're teaching high school, you have a box like this. What's the first thing the students do? It says do not open, right? So you want them to get kind of curious about it, but you don't really want them to open it. All right, see if I can make this work. There's a double dog dipole. And it turns out that a couple of hot dogs in line, in fact, these are the long ones. I have to touch them off. They're almost like halfway, 432. And because they are full of minerals, things that you don't even want people to know that you're eating, and they have a lot of surface area, they conduct fairly well. Now, the surface area spreads the electrons out, so they have more area to work on. As you go up in frequency, electricity tends to spread out more on the outside of the conductor than all the way through. That's why elements for antennas can be hollow tubing, because you don't care about the inside. Why waste metal? Just make hollow tubing. Now, I don't know what happened. They call it the skin effect. I don't know what happened to skin with strike curves. Anyway, this polarized. But so I noticed that the ends don't pick up anything. The ends pick. Well, it does have that dipole pattern. That's called a double dog dipole. And if that one, the Dilly dipole. Now, they are physically a little bit shorter than a half wavelength because when you make an element fatter, you have to make it shorter than different. It isn't perfectly tuned. I've been using these same pickles for years. I stick them back in the jar, and Mickey wrote bad on them, so we wouldn't eat them. But these things are probably 10 or 15 years old. Now, this is an example of VBT. What VBT stands for? Vinegar-based technology. So this is Dilly dipole. Now, why does the dipole made on a pickle give off green light? Hot dogs give off green light. Tell me. Tell me. So this is fun to do. I mean, K1WHS, the big VHF guy, when I was playing with it, I had one of these pickles in my window. He's in Maine. So he's like 50, 60 miles away. So he put up a couple pickles, and sure enough, he were really loud at 432 megahertz. Pickle to pickle. So there is if anybody wants to beat the record, the distance, there's a Work on Pickle Award. I will hand the letter if somebody wants to try this and beat the record. But, for some reason, most people don't want to do this. I don't know. So, the hot dog thing, I, that, I don't know, we take quite a few. I made a graph. Now, this is something that I should get a scientific grant when they restore the grants. Or this is antenna efficiency versus nutritional value. All right. Now it turns out the worse the hot dog is for you, the better it is for the antenna. Just look at the ingredients. These horrible things. They're full of salt, nitrate. So if you're going to do this, don't buy expensive hot dogs. Buy these real cheap ones. And so you can continue the work in this. I haven't. I don't want to waste a lot of sugar. I haven't tried that. No. Now we all right. Now for UFM people that use vertical polarization, here's the Saturday night special. This is B&M beam. It has to be B&M. That's the bottom half of the dipole, and that's the top. And this, remember how I showed you how the dipole is directed? In this plane, the vertical plane around the horizon, it's omnidirectional. So you could put this on your car and drive around and pick it up. The ends, you'll get those overhead. If you're a new ham, try building one of these. Stick it on your car, drive through Bedford, and see how far you get without being stopped. Again, hot dogs, red light. So I don't think B&M beans are as good as they used to be. Somebody else knows. Maybe some of the other cans would work just as well. So that's the Saturday night special. We used to eat hot dogs and beans every Saturday night. Still do. So, all right. So any questions on hot dogs and pickles? Chris, you gotta help me with this. Get the pickle and go back to another town. Make sure you run it so everybody can see it right. Right. You're lighting up. You're splitting out. There it is. Is it working? Can everybody see it? Okay, I'm gonna, I'm gonna put power down a little bit. Okay, 1, 2, 3, 4, 1, 2, 3, 4. Hello, 1, 2, 3, 4. That's the talking pickle. Hello, 1, 2, 3, 4. 1, 2, 3, 4. AF1T, the talking pickle. And if you don't believe it is, you can use the crystal radio and hear it. I was doing this one when the house was over here, 2 miles away with it. So you can make talking with it. Now, somebody asked how much power you can put in a pickle. How much power you can put into a pickle? Want to guess? I don't know. The regular ones are usually smaller, so probably not so much. Uh, I ran 90 watts when it ran cool as a cucumber. That's a keeper. Yeah, I use that joke over and over again, but I made it out of gherkins with little that way. Yeah, I actually did that. I had some sliced pickles, so they acted like capacity loading pads on the edge. That actually worked. So you can have fun with this stuff. This is a good thing to show kids, you know. Some of the school students should be doing this. Might help them get interested in science, or at least weird science. All right, now back to dipoles. Remember I said that dipole had a capture area on it? See if I got enough power coming out. Yeah, no, I'm going to crank it up for maybe 4 watts, something like that. All right, so these are smaller lamps, but I didn't have enough of them. They can say, oh, that's not enough. All right, here's another one. Now, if I put 2 lamps together within the cone of transmission there, I should get twice as much energy, which is 3 decibels. Right? 1.26 times 1.26 times 1.26. 3 decibels is like doubling the power. But what happens if I try to run them too close together? They rob power. Each one is territorial. It has an area around it. It's like a neighbor. You don't want to be too close to the neighbor. Okay? So, well, these things, if you get them, that's the distance. It's about 5/8 of a wavelength, a little over half wavelength, where they capture areas just barely intersecting. When you put them closer than that, they overlap and you don't get the full doubling of your power. 3 decibels. So that's why when you stack antennas, you don't want to have them too close together. They're not much better than one antenna. Looks impressive. More aluminum up there. We remember seeing those CD trucks with the verticals that are only like 4 or 5 feet apart, which is very much less than a half wavelength. 11 meter band. Well, those look pretty, but they don't work much better than one of them. So that's how stacking is. You want to increase the gain of your dipole, you can put 2 of them together. No, I'm going to have this one. And put a light bulb on one of them. Let me find a light bulb. And this is a brighter light, so it's probably going to take a little more power. So what you're going to do is hold this thing here. This is a power combiner. It takes two 50 ohm antennas and combines them and makes a 50 ohm filament, feeds them together. And I've got a light bulb for them. So you're going to stand behind me. And I am going to, you can hold like that so everybody can see it. Now, each one of these dipoles has, everybody see that? Each one of these dipoles has an equal length of coax cable going through it. Called a delay, but the delay is equal. So whatever I have coming in one end is going to be shifted in phase by the same amount. Let's see if I can get them to light up. Get it back. Light it up. All right, let's see if I can find it. Here's that 5/8 wave thing. Everybody see that? All right, now what happens if I move one closer? What's happening? They're out of phase because the physical distance between each antenna is not equal. The cables are equal. So the signal will reach the light bulb when the sum of the distance in wavelengths and the delay line and the quarter wave inside the power divider is equal for both of them. So if one of them is ahead of the other one, it's like people in a race. Don't give one a head start, you might win the race. All right, I'm going to move the other one down. Right? If I move it up this way, it goes away. Down this way, it goes away. So remember, the dipole by itself worked no matter what I did. But when you put two of them together, I'm going to get gain here because I'll get two antennas, and I'm going to get loss there. So this antenna, because the wave is maximum perpendicular to the plane of the two dipoles, it's called a broadside array. That's an old time term for antennas. Broadside. An array means two or more. Right? Now, if I flip them around, what do you think might happen? Right. Ah, one of them is backwards from the other. Notice one's got a red end and one has a green end. The red end goes to the center of the coax, the green goes to the field. But they're out of phase right now, so you don't get any energy. However, if I go this way, they are now in phase. So when I put them this way, they were out of phase. When I put them this way, so notice the energy is in line with the plane of the elements rather than perpendicular to it. So that's called an end fire. So those two words, end fire, means you're in the plane of the elements, maximum energy, and it's bidirectional, meaning it works this way. So you can make one of these aimed towards Europe. It'll probably be good to the west coast of the U.S. Probably not so good towards South America and the Arctic, but it'll cover a good part of the U.S. plus Europe. So that's a bidirectional, two direction. Right? So that's an end fire, and this is a broadside. Right? You already got that? I wanted to show that. Now there's some other fancy things you can do. If I get this here, I'm going to add a delay. I'll say, let's put a quarter wave delay. I can do it right here. It doesn't matter. Or you can put it to it. Put it to right there. I'm going to make one longer than the other by a quarter wave. Remember what we're talking about. They're in phase when the length of the delay line electrically, the distance from the source, all add up to the same thing. So he's adding quarter wavelength in this thing. We want to predict what might happen. I'm getting. I had to move this one closer, the top one closer than the bottom one. Why? Anybody want to tell me? Get them in phase because I've added a quarter wave here, right? So I have to make up for it by putting this closer. It's like giving somebody a head start in a race. If I go the other way, I can also go backwards. Get them in phase. I had to go back 3/4 of a wavelength to make up for that. So there's all kinds of things you can do. You can steer the beam essentially. All right. It turns out that that distance is now decreased. The top one is now closer because I'm aiming downhill. So the path on this antenna is shorter than this one. That makes up for the delay line allows you to steer the elevation beam up within the kind of neat. Huh? K1WHS did this on 6 meters. He's got all these delay lines. You can add whatever angle the signal from. You got to be really into 6 meters, all right? But you can do that. If you live on top of a hill and everybody you want to talk to is down slope, you could do what I just did. Or if you're down in a valley and everybody's up on the mountaintop, you could put the delay in the other blade, aim it up there, right, like this. So you could do fancy. That's just a quarter wave. I don't have time to show you because I had different delay lines how it changed the angle. But I want you to get the idea. All right. Any questions on that one? You know. Um, what else can we do with that thing? Quite a lot. I don't have that light bulb back. We could do the same thing with the Aggie. All right. Now suppose you're on 80 meters and you want to put up a dipole. How long would it be, everybody? 100 and something feet, right? How many feet they have? Ooh, a lot of people don't. Feel like 130 feet, maybe, something like that. And they have, well, it turns out that with a dipole, most of the radiation is in the middle where the current is not so much at the end. If you look at that little picture, the ends of the dipole have very high voltage on them in the transmitter, and the current diminishes to near zero. In the middle has low voltage and high current. So, but the middle contributes most of the radiation. However, you need the ends to do it, to make it resonate. But you could bend the thing so that the middle predominates and make it shorter lengthwise. I'm going to get rid of this and put that. Use this so I'm not going to have it. There's a dipole that's bent at the end. Now, the ends have high voltage. So if you picture this 130-foot wire on 80 meters between two trees, you got to be careful that the ends that are hanging down with a high voltage don't hit your family or your pet or something. If you have a neighbor, you don't get along with that. Right. So you got to be careful with that. But it is one way to do that. What are you giving up? It turns out that the antenna becomes lower in impedance. You know, in space, it's like 72 ohms. This may make it closer to 50 ohms. However, the ground affects it too. So that has an effect. But also the bandwidth, frequency range over which it works is slightly different. That work over many kilohertz band. So every time you make an antenna shorter, you get up. Otherwise, we all be doing it. So that's one way you can do it. Another way is to put loading coils and little capacity hats, look like an X on the end. You might have seen these for mobiles. You couldn't run a dipole on the car for 80 meters of size. It's too big. But you could put a conductor in it. There's loss of it. It also narrows the bandwidth. So here's a dipole. I'll tell you the difference. With loading, this bandwidth is very much narrower than the first one. Now, when I made the bread and butter pickle antenna, I used bread and butter pickle slices on the ends with the capacity. You know, but working. It worked. It worked. So there's a lot of things you can do like that. The dipoles, a lot of them are limited to by imagination and what you're trying to do here. See if I can get this light bulb out. You want to come off. You get it. Right. Here's one. Here. Anyone tell me what polarization this is? This is, I guess, horizontal. Anybody else? Let's try it. Now that's horizontal, so we'll see which way it matches. Happening. The high current part in the middle, most of the radiation. The two ends, the current splits. One goes up, one goes down, and they cancel each other out in space because they're pulling in opposite ways. Kind of like two people pulling in like a war, right? So the currents contribute to no energy this way, that gravity, but that so it's deceptive because these are longer than it. Notice I had to make this part shorter to make up for the fact that these are longer. So it's kind of like a double port tongue kind of a value. Why would you make something? Well, suppose you had two skyscrapers. You don't have much movement between them, but a lot of height. You could hang one from one skyscraper to the other, maybe get your horizontal dipole on 80 meters and couldn't quite fit. That's a weird situation. You could also make a vertically polarized antenna that you don't have physical room for, like you want to get on 160 meters. And the town doesn't let you put up with 200 foot wire. So you put up a short one, but you put loading on the top. It's a T-shape. Now that's vertically polarized. So horizontal. A lot of people on those 60 meters in the middle and use vertical polarization because it's easier to do it. You can run this as long as you want to make it work. So there's all kinds of schemes you can do. Now, how many people here have an antenna on the G5 LV? Well, what happens if the antenna is more than a half wavelength? I've got one. Maybe it's kind of there's a little LED. Right, I'll take the one off of the beam can antenna because that's a nice one there. And I've got a nice red LED, and I got this will count easy. I've got to put this. See what this will do. All right, on broadside, but with the dipole, it picked up the most energy. This one doesn't. Happen. Kind of peak, but not at right angle. Right, right. Have another piece. I don't like that. I'm going to person. I'm going to try the other light bulb because I should do. I think I left the connector on. It's in my box. So we don't get it in a second. I get it. This thing is kind of a. We'll find it. Think of any questions while I'm finding the connector group. Not that one. I don't know what happened to it. Not there either. So, I know what happened to that. There's a double BNC. So that's double BNC connector. That's my thing right there. Maybe in here. Okay. Think of here it is. This is what I'm looking for. Yeah, well, it was the opposite of that. Was that on one of the cables? Yeah, leave it on that because I need to have one of each. Here it is. Here's one of them. Let me grab the hot dog antenna. Right here. Go back to this. See if this lights up better. This is an okay. There we go. This is much brighter. An LED is much more sensitive than a incandescent light. So to go further, however, it's not faster. Okay, now what's what happens? There's a null there at right angle. The null there. But there's a peak right there. There's another null there. There's another peak there. There's a null perpendicular. There's another peak there. And there's a null there. It looks like a four-leaf clover. Everybody see that? Four-leaf clover. The pattern is not the same as the dipole. This is two dipoles, end to end. There's one and the other. It turns out that when you go from one half wavelength from the end, where the voltage is high, you get another high voltage point here, but the current reverses the negative. So during half the cycle, the current might be going this way on this half, but it'll be going this way on the other half. And the other half of the cycle, they reverse. And I show it on a lot of my diagrams and my talks with little arrows. They reverse every half cycle. Because of that, because the current reversals at right angles now, unlike the regular dipole, you have a null instead of a peak. But if we go somewhere on either side of that, we've got a different distance between this dipole and that dipole, as well as a phase difference. And if you do the math, which I don't want to do, you can show that you get the peaks. The four-leaf clover. You can carry this thing. So this is an antenna that's one wavelength long. So unless you take some provision to put these two halves back in phase, you'll run into this problem. And you can carry it to an extreme. For example, there's one that's four. There's a peak. There's a null at the end. There's another peak. There's another peak. Another one. Another one. Turns out we get 8 leaf. Actually got 8 leaf clover. Instead of four, we get twice that. We get every half wavelength the current reverses. This one goes that way, that way, that way, that way. They're all out of phase because you got two going one direction, two in the other. So at right angles, they're out of phase. But at some other angles, because of the distances, you'll find that there's some peaks. If you use a G5RV antenna, a 40-meter G5RV, which looks like that, close to half wave on 40 meters, it'll look like this antenna. And that's great because you can work people, but on the other hand, there you got 49 states contact, and the 50th one happens to be in one of these nodes, the others weren't. You might be spending a lot of time waiting for permission to get that. So it's an antenna that has directionality, but it's not all in one direction. I kind of liken this to the Outback, like the blooming onion with all these little spikes all over it. Kind of like that, except it's in three dimensions. Because if I move it this way, with the same effect, these globes would happen this way and that. Who knows what you're going to do? There are enough people around the world where you're going to find somebody to talk to. It may not be the one you want. so that's an example. So knowing this stuff, you have to think about what you're going to do when you have an antenna that's more than a half long. One way of doing it, you can do something like this. This would be the type of thing you use on community radio. Instead of having three waves that are alternately in and out of phase, you can put these little delays. So they give you the 180-degree phase. And that puts this one and this one back in phase instead of out of phase. And this one puts this one in. This should happen. It's a nice clean one lobe pattern at the horizon, not with a null horizon. So it gives you all the energy in that direction at the expense of those up and down globally. So we did that by phasing. And there are many ways of doing this. All those vertical repeater antennas and things you see have some scheme like this. Sometimes they bend this around in circles. Sometimes they make them out of stubs that are placed in cable, all in a radome, fiberglass tubing. There are all kinds of schemes for reversing coils. So that's an example of tuning the thing. Even though the other antenna radiates, you don't know what kind of radiation pattern it has unless you control it. So, well, I've got this subject with remember that typo? Suppose you put two of them together, and again, I find that little rarely do them. Suppose I put two of them together like this, one this way, one that. I can make a quad, two quad named four sides. Each side is how long? Each side. Quarter wave, right? Because a half wave is this eighth wave, this quarter wave, that gives it the total. So there's your half wave dipole, there's your other one. And let's see what it does. I have a whole topic we just on loops. There we go. And that is horizontally polarized because this part, that part have the high current points. This part and this part, remember the current reversal? That's going to be here and here. Those are the high voltage points. So the current's going down here and up there, or up there and down there. But whatever it is, each side is the opposite and they're working against each other. So we're going to get energy in that. So if you want to make it vertically polarized, you have to feed one side or the other. So that's a quad loop. Now these antennas kind of neat to build and they're easy to make them. And they're shorter. You might find a situation in your house where you have a couple of trees that are like this apart, but you could hang a couple of wires like this, and the bottom would be lower to the ground, so you don't lose much paper. And you're going to get some gain, not too much, but some gain here, because they're not a 5/8 wavelength apart. So you don't get the maximum gain that you could out of two diamonds, but you get quite a bit. And you don't get as much energy up overhead. So you're not wasting it there. So you're putting a little more energy. But the gain of a quad is going to be 1.5 dB or something more than a dipole. So if I remember the reflector scheme, I could take this quad and put a reflector behind it, which is a little bit longer. Working? Yeah, there it is. There's a reflector. And it's in the shape of a tube, sort of. About a quarter wave on the side and a quarter wave spacing. So we call it a tube, but they don't have to be a square. It could be another shape because I can make anything I want, 432 megahhertz. But on HF, we've got insulators and that sort of thing to worry about. But you might find at your house that something like this might work better because you have one tree. So you can hang that from the tree, and then you can hang ropes with stakes on the ground and make the diamond. What's this part and that part is, and there's your high voltage parts. So you have the high voltage. You don't want to have these parts not, really metal. In fact, in the back of your old TVs, you used to see these things. Where you reach up a little bit smaller than this around. This gives you the most gain because it's got the biggest area for the amount of wire. Most gain. That's a pretty good antenna. Here's one that I really like because it inherently wants to be very close to 50 ohms. It's most radios like the C. These most hand radios. And it's longer than it's tall. In fact, it's about twice as tall this way as that. So that would make this a third of a wave. That would be a sixth of a wave. You add a third, a sixth, a third, and a sixth, you get a wave. So two dipoles. That's close to 50 ohms. Right? Well, one advantage, you can make one of these for 6 meters, for example, where a dipole would be about 1 feet long. Now it's a little over 3 feet long. So you could make a pipe out of PVC with a couple of spreaders, one here and one here, made out of those hybrids, those fiberglass rods, in the driveway. Then if you get they come in 4-foot lengths, you only need about 3.5 feet. So you don't have to worry about hanging the ends of a dipole up in a tree. Only needs one support. You need the height. Height's going to be about 6 feet. Very simple antenna to make that works without much fancy tuning. Highly recommended by me. All right. All right. Any questions on that? What else can we do with dipoles? Here's a dipole, but it's a different. It's a ground plane. It turns out some of the antenna I showed you with a beam tape. These quarter wave radials act like the missing part of the dipole. This is vertically polar. So there it is. And it's omnidirectional toward the horizon. Same a lot of stuff. And it's got a knoll on the top. So it has a pattern like a donut. Over the middle goes up that way. So if you don't want to have a rotator, have a aiming engine, especially when you're driving a car, then you could use. Now the bottom part, the radials, there's a question on it for the next one. I don't think still asking. What's the purpose of that angle? Why that angle? Turns out that if you change that angle, you can make it match the 50 ohms. Because if you have it down vertically, it's more like 7 ohms. If it's horizontal, like 30 something ohms. But somewhere in between, you get the 50 ohm match. So you can actually play with that angle to get it. The lens is off. So the beam cam took the place of these. You can use the roof of your car as long as it's metal to do much the same thing. As long as the roof is big compared to the way it will act like don't want a mag mount antenna on a piece of wood furniture. You need some sort of a ground plane or something to take the place of the radios. You could use a cloud cabinet. Don't put the antenna without that because you get one antenna. You might wonder it doesn't work. So, any questions on that one? What else can I do with dipoles? There's another example of it. Here's one in which there's two dipoles. And they're right angles to each other. And this is also pretty omnidirectional. In other words, in this direction. Unlike the regular dipole, where there's a null off the end, it turns around and kind of makes up for it. There's a quarter wave delay line between them. This would be useful for something like on a satellite, somewhere in space, or want it to be either on or off in this point of the year. And this is omnidirectional, at least in this sense. This sense, not so much. So that's called a turnstile. Most of these antennas have names. So resemble something that there's all kinds of schemes you can do. Oh, I don't have much time, but I think it's time to quit here. So a couple things, and then we'll time to leave. Oh, there's two dipoles in phase. This broadside or incline? Buddy? Huh? Broadside. The signal is perpendicular to the plane of the dipole. Incline doesn't work because this one, they're halfway apart, so they cancel in that direction. And the delay lines are equal, so they should be in phase. At least in this one. Here they're not in phase because this one's further by a halfway back. Now you can combine many of these things in arrays, branches of branches to get you more and more gain, and that's a whole other topic. So, lastly, I'm going to show you the Aggie thing. I showed you with the reflector. So here's one that's ready made. If you put a reflector behind it, you can pick up the signal, but if you put a reflector in front of it, you block it. But if you make an element that's a little bit shorter than the reflector, directly, it's this one. Now the antenna works in that direction, it's not working. So this is a unidirectional, one direction. This might be aimed towards Europe. I'll have a null to the people on the West Coast. At home, I have a pair of Yagis, 10 meters. I can switch between the West Coast and Europe without having to turn it. And it's quite a difference, like 30 dB. It's 1,000. Because one antenna is going to Europe and one to California. So there's my Yagi. Now the difference, if you can measure it, between the signal in the front, signal in the back, is the back ratio. And you can measure it exactly 180 degrees away, so it might be good. some people use front to rear with, so they consider the whole hemisphere behind it, not just that one point 180 degrees away. That's probably more useful. But what's a typical good AID have? Front to back ratio is usually frequency dependent. It might be great in the middle of the band. You can take 20 dB across the entire band. 20 dB is a heavy time. And see, I can detune the thing. It can also worsen the front to back ratio. See the signals coming back here? I just detune the reflector in the director. So I'm letting more signal in the back. I'm detuning. And I could have played the same game with the two Yankees that I showed you with the one last one. I know this one. The Moxon. He knows because he's got a Moxon is a two-element Yagi. But the elements are shorter because they're bent. So this is a reflector. Notice that there's a little gap there. This is just on the two. And those elements, the reflector is longer than the ribbon element. It turns out that it has a couple of advantages. One of them is it's shorter. So if you're on 6 meters, you can actually carry this thing on the top. With the 10-foot on the thing. Really. But also, it turns out that if you make it right, it's very close to 50 ohms. So you don't have to have any constant branching speeds. And it has less gain than the 3-element Yagi. It has a very nice null off the back. In fact, I think a cardioid kind of pattern with the heart shape with a null on the back. And it's got a pretty good front to back ratio compared to many 3-element Yagi. However, notice I'm getting stuff off the side. So that's called a Moxon, or Mr. Moxon, and it's become a very popular antenna because it does a lot. So I could stop here, and I think I will. I keep looking at stuff. Oh, another whole top. Loop antennas. People are playing with these magnets, little tiny loop antennas, tiny in terms of wavelengths. Because on HF, you don't have much room. You can make a fairly small, just a 2 feet diameter loop antenna that get out. And it has some advantages. But this is a small loop with ortho megahertz. It's a dipole. It's shortened, but you need a capacitor to do it. The more you shorten it, the bigger the capacitor has to be. And it has a fair amount of current going all the way through it, so it's fairly omnidirectional. It's probably make it the more perfect that it is, but the less velocity. And there's also a null off right there. So this one is under a half wave, but I have a whole other talk this time. So lots of stuff. Any questions before we get going out of here? Dipole. It's like a letter J. It's a dipole. But it's not 50 ohms because it's fed at the end where it's maybe 1,000 ohms. So this little quarter wave matching thing allows you to match anything between a few thousand ohms here and 0 ohms at the bottom. And you can drop it down and find the 50 ohm point. There you go. So it's another way to make a dipole. Okay. All right, I think I'm going to quit. And I'll pass around the picture of the pickles that received the signal from the Arecibo dish in Puerto Rico. Same pickles is in the shot. And I actually heard the signal, and the guys in Puerto Rico thought it was kind of neat. Anyways, Mickey and I contacted them, but we did not transmit it to them. All right. I guess I'm overstayed my welcome for this thing. Thanks so much, Dale. Thanks for coming by. Go out and experiment.